3G, 1X, video, it could be UMTS, and also the local technologies like 802.11n, and these networks will be typically operated by different service providers. On the client side, you have again diversity in terms of capability. You would have PDAs to laptops capable of multi-interface radios. You could have those capable of 802.11 built into it, and you could have a set 3G card like the laptop that I'm using right now. Right? Using a multi-interface, you want to be able to transfer roam from one to the other, and be able to access your favorite applications, be it streaming, email, could be corporate VPN. And at the end of the day, you still want to have one common bill, preferably from one provider. So you are not interested in creating 10 different customer relationships, but you want a single bill. And as you roam, there are two things that need to happen. First, you need to be able to get a common bill and common set of profile credentials. You need to be efficiently authenticated to a common backend. And you also need sort of the intra-technology and inter-technology handoffs. So for this to work, and to have a common service across different networks, you need sort of a uniform service mapping. So when I go from UMTS to 802.11 or from 3G 1X to 802.11, if I have a certain service profile, I'm a gold customer on one provider, that should be potentially preferred on another network also. So that sort of requires you to establish roaming agreements. So in the complete the picture, you have the whole slew of things, starting from the client right up to the provider, where you have multiple providers which are talking to each other using roaming agreements to create a unified, integrated public wireless network. Now, when you assume that this picture is how the world is going to be in future, you need to address the things that I was talking about, the authentication, the mobility, the new way of doing network architecture, things like that. So once we assume that 3G and 802.11 are actually going to coexist, not necessarily try to kill each other, you need to sort of answer the question, how am I going to integrate them? What are the integration architectures that make sense? So before I go to those specific architecture, I just want to give a quick summary just for the sake of completeness. Again, all of this is probably very familiar to you guys, so we don't need to go into too much detail. 802.11 network, you have a typically access point to which the mobile nodes are talking, and the network is characterized by ESSID. You have anywhere from 1 megabits to 54 megabits per second over a low range radio. The key point to note is that in the legacy 802.11 you had the broken web-based authentication, but now going forward you will have the 802.11i, which will support two different variants of access, the wireless protected access 1, which uses a new form of encryption and new form of computing MAC code on the packet, and sort of the full-blown AES based WPA. And these keys that you require for encrypting in WPA 1 and 2 are typically based on a shared secret that is stored on a remote authentication server. So be it a home location register, could be a home AAA. And that authentication exchange will typically happen using a protocol like 802.1x. And this is sort of key to remember, because when you try to do interworking, you have to account for these things. So the 1x RTT, again I'm showing this as an example network. You have a bunch of base stations to which a mobile node is talking using this CDMA protocol. Per carrier you can get, right now in the live network you can get 144 kilobits per second peak throughput. Bunch of base stations are then aggregated using a radio network controller, to which the mobile node sort of maintains a layer 2 connection that is guaranteeing error-free packet transport and also resource management. So that's the radio link protocol. And if you are doing voice calls, the RNC is typically connected to a mobile switching center that is then connected to SS7 network for the signaling part to a home location register. So when I make a voice call, the signaling path goes all the way to the home location register and my call gets admitted. But for the data, you have a new packet element called packet data serving, or the PDSN, to which multiple RNCs are aggregated. and the mobile node maintains a layer 2 connection, that's a point-to-point protocol. And the PDSN then supports two different modes in on this PPP connection. You could be either doing mobile IP on top of that, or you could be doing simple IP mode. So when you move from one PDSN to another, typically you'll be doing the mobile IP mode is supported as is supported in, for example, Sprint network. Sprint, right now when you get a card from them, mobile IP is right on the card itself. But Verizon still operates in the simple IP mode in most places, but you can also find mobile IP in their case if you use co-located mode on your end host, right? So that's sort of the complementary data path for the 1x RTT network. So now, if I want to integrate, the simplest way of integrating would be creating a 802.11 integration gateway and dropping it in the 802.11 network and connecting it directly to the 3G packet transport. So in this case, in case of CDMA 2000, you have connected it directly to the PDSN node. In case of UMTS, you are going to connect it to the GGSN. So what has happened is, in this particular case, the 802.11 cloud appears to the 3G network as just yet another radio network. It treats it as yet another radio transport. So to the PDSN or GGSN, this cloud appears as a packet control function or a SGSN in the UMTS 3G PP2 terminology. And if you are doing release 6 UMTS, that link between the gateway to the GGSN could be IP link. It could be packet over SONET over IP. If you are doing the current release 4, it could be an ATM link, right? So in principle, this is a very nice, very elegant way to do things because it has advantages from the point of view of a 3G provider. As I said, it appears as yet another 3G radio. So it requires minimal changes to the client in theory at least. You could use the same authentication infrastructure that you are using for your existing 3G customers. You can easily generate a common billing statement. And as far as network management is concerned, 802.11 appears as just yet another access network to manage. But if you take a closer look, there are too many disadvantages that one has to go through and cater to before you can do this kind of tight integration. And we call it tight integration because your data path as well as your authentication path for 802.11 access is going through the 3G network. Right? So first is traffic engineering. Typically the 3G cores are very well engineered. Right now a single base station typically has a T1 link coming out of it. Not anything bigger than that, maybe a few T1s, right? So as soon as I start connecting large number of 802.11 access hotspots into the 3G core, the load on this 3G core will dramatically increase, potentially 25 times to 100 times more based on how much 802.11 you actually going to deploy. And believe it or not, a lot of these 3G cores are actually fairly well fine-tuned networks. So you have to go and re-engineer this and also ensure that because of 802.11 your existing 3G traffic and voice traffic is not getting affected. Now,
a question: what percentage of the 3G network is the wired core in terms of capital?
Wired core? Oh, you mean the total infrastructure investment that goes in?
If you say the total infrastructure, you know.
Historically, the T1 that you route into the base station location tends to be a sizable chunk of the infrastructure, especially because the RBOCs have traditionally kept the T1 TC prices high. Hopefully going forward, as the so-called Metro Ethernet thing catches on, you would have fatter pipes available at a cheaper rate, and then you could also have a transition to more IP-based connectivity to the base station rather than more a T1 connectivity. IP sort of shows a way further into the network right now, right? So it is right now a significant cost of the network layout. I don't have an exact number, but if you want, we can certainly, I can try to get that number for you from some of our sales marketing people. So ideally, if we take the tight integration approach, the client software is going to remain unchanged. You are going to use the same 3G stack on the 802.11 access. So that requires you to go and define these new 802.1x authentication types, and that requires you to change your client to support this new EAP type. So it's not going to be necessarily transparent 3G software that you otherwise use on a 3G network. So when you go to 802.11, you have to cater to the 802.11i standard and the specific nitty-gritties of it. Also, if you are doing current release for UMTS, your 3G authentication requires that your WLAN gateway be aware of the VLR infrastructure, the HLR, VLR, the SS7 infrastructure. Also, the ciphering keys and the integrity keys that you have in 3G may not be directly usable in 802.11 encryption. Believe it or not, for a provider, actually this turns out to be a very bad option, because if you are a 3G provider, you have to own this 802.11 infrastructure, because it is getting connected directly to your 3G core, right? If it is not operated by the provider, then the guy who is operating this 802.11 infrastructure now essentially has to have physical connectivity from this network to the core of every provider that he wants to have a roaming agreement with. And if he doesn't do physical connectivity, you essentially do IP tunnels, and those IP tunnels make your routing extremely inefficient. So bottom line is that if you do tight integration, the only model that you have is that the guy who deploys 802.11 is the one also owns the 3G network.
In your tight implementation, you mean the routing protocol between TGSN and 802.11 base station is a link layer, so not the IP layer?
Yes, so because we are making the 802.11 radio network look like as if it's
so
right?
No IP layer protocol routing.
Yes, that's right. So if you, and primarily because the provider cores are typically non-overlapping. We haven't gone to a stage where you have one common IP backbone transport that Sprint and Verizon and T-Mobile are sharing. Typically T-Mobile, Verizon, Sprint, they have their own transport, at least a large part of it. So because they are non-overlapping, you can't go and have a single outgoing pipe out of your integration gateway. And if the 802.11 network wants to support non-3G customers, then you have to account for those separately. And their traffic also has to go through 3G network, even though the customer may not be interested in the 3G service at all. So in some sense, it doesn't make any practical sense, even though it sort of, on the face of it, appears to be a elegant solution. So loose integration architecture is what makes sense. And when you go through this, you will realize, yeah, this is so simple. Why didn't people think of this right away? Believe it or not, Verizon and other providers initially thought of doing integration using the tight integration approach. So here what you are doing is you deploy the 802.11 integration in the 802.11 hotspot just the way as you did, but instead of connecting it to the 3G core, you are connecting it to the public internet by a commodity link. And we call it loose integration because you are separating the data path and the authentication and the billing path. So when a Verizon customer roams into this 802.11 gateway, you're still authenticating him to the back end of Verizon. So you still sort of send the authentication traffic to Verizon's home AAA. But the data traffic never really goes back on the Verizon network. It always goes through a commodity uplink into the internet. So that's why it's the so-called loose integration. And again, the link between the gateway to the internet could be either a layer 2 metro Ethernet kind of connection, or it could be a layer 3 routed connection to the internet. So it's not imposing a layer 2 connectivity like the tight integration requires. And you are allowed to have roaming contacts with anybody that you want to. So you are not necessarily tied to a particular provider. So not only that, you could, when it comes to authentication of a user on the 802.11, you are not tied by a particular 3G authentication scheme. There are new authentication schemes, one of which is I'm going to try to talk about shared key exchange, and then there's AK and SIM. These are specifically designed to allow you to authenticate a 3G customer on a 802.11 network. And it's designed specifically with 802.11 in mind. So the 802.11 gateway will essentially support these schemes, will collect the billing records, and offer some features that I know I'm going to talk about in the prototype implementation. So IOTA is sort of our effort to build and demonstrate this loose integration. And in our current prototype, we have 802.11b, 1xRTT, EVDO, and also UMTS. It works in the lab, but 1xRTT and EVDO we have been using it in the live network of Verizon and Sprint also, and anywhere that you can find CDMA networks you can use our stuff. So it implements loosely coupled architecture, and we have this so-called IOTA gateway and the multi-interface mobility client. So the gateway consists of several parts. So it has the IP component, the web services, the mobility management, and authentication and accounting. And these different modules, they share an active session database. So if there are a certain number of users, each user state is captured in a session database. And because this database is sort of persistent database, if the box goes down, it will come back up and try to restore the user state. So try to sort of give you harder QoS guarantees in terms of session continuity. And also there is the IPC service that these components talk to convey events to each other. The data packet, the data path that currently we have is primarily for supporting NAT full firewall functionality, the quality of service which I will describe what it is. Then also the traditional IP forwarding and packet mangling. And it's currently implemented entirely in software, but we are also looking into doing it in network software, network-based processors or hardware. And the rest of these modules are all in user space. So the IOTA packet filter that we have is essentially for doing things like NATing, firewalling, doing certain kind of authentication functions, and it's all based on Linux IP tables. We also have a full-blown implementation of mobile IP, foreign agent and home agent that's resident in the gateway. We also have a full-blown radius server that's a part of the gateway, and it's all running on that small box over there, all of this functionality. And it has the standard accounting function as well as local radius authentication and radius proxying. So it supports, I'm going to go through this part just quickly. So it supports 3 different authentication models. It supports so-called web authentication, which hopefully you will see when I do the demo. It supports a mobile IP level authentication for mobile IP registration. And also it has ability to talk to SS7 gateways at the back end. So if you are a singular customer roaming into the hotspot, you will be appropriately authenticated to a SS7 cloud. So basically it can support layer 2, layer 3 and layer 7 authentication, and they can all coexist and they can be configured based on any policy that you want to have. So you can require that only a layer 2 authentication is done and others are skipped, or you can require all 3 authentications to be done, or you can configure that thing in our box. So the quality of service mechanism that we support is actually at layer 3 and above, and it sort of coexists with what is being done in layer 2 in the 802.11i standard. So this work is sort of coexisting with 802.11i, or it can also run in legacy 802.11 installations. So if you take a closer look, you want to support quality of service on the bottleneck link that is going out of the gateway into the internet, and also on the air quality of service. And in our current case, we support sort of class-based QoS, again configurable, gold, silver, and bronze, and you can offer minimum rate guarantees. So if you are a gold customer, you can be configured to have certain peak guarantees, and you don't need any special client software for accessing this quality of service. If you add quality of service client, then you can do even better. One important point to note is that because this gateway handles multiple access points, to be able to allow fair access to this link, the gateway has to know the mapping of each of the 802.11 cell as to how many gold customers, how many bronze customers, how many silver customers are in each cell, and proportionately allocate bandwidth on the link going to the internet. So this gateway actually probes these access points to be able to collect information about which customer belongs to which cell. So it creates a cell map, and based on that cell map, it does bandwidth allocation. And it's also capable of doing standard list marking and traffic policing. And again, in this particular demo, I don't have time to do the QoS demo, but because I need another workstation to show the monitoring window where when customers come and go, you can see the bandwidth getting appropriately shared. So one important point is that this has a full-blown web cache again on that tiny box over there, and that allows you to do content caching or stream caching and also do a local portal. And one interesting optimization that we have implemented is that this web cache is actually mobile IP aware. So to understand what I'm saying, let's go through this animation here. Let's say you have a client that did have internet access to the website over here. That access is trapped by the layer 4 switch in the box, and it goes to the web cache. The web cache goes to the external website, so that results in an internet access on this link over here, right? And then again, the traffic comes back through that link. If you are operating in the mobile IP mode, the cache is going to think that you are actually on a remote network because it's sending it to your home address. So the traffic will go back out again on the internet to your home agent and come back. So instead of actually saving a network access, you have ended up doubling the usage of the uplink. And the sort of the obvious solution for that is that you make the web cache aware of the mobile IP agent. So when the cache goes and gets the data from the website, it knows that this guy is actually local to my hotspot. He is sitting locally. So it gets the data and then just forwards it internally into the hotspot. So it just injects it into the local foreign agent rather than going out to the home agent and coming down. And of course, this has a drawback that if you move from one gateway to the other, the foreign agent, the web cache thinks that if it's not informed, it will think that it's sitting still on the local foreign and it will try to inject it over there. So the inter-gateway protocol that we have between the gateways, you could convey that information. Hey, the guy who was sitting on your foreign agent has come to me now. So you can do local forwarding rather than going to the home agent.
But each cache has its own timer, right? If timer expires, then you can give it.
Yes, I was primarily talking about long-lived flows if you are doing any long-lived video forwarding, say audio forwarding, right? In that kind of a scenario.
Normally in that case, there is no caching, right? In streaming.
No, I'm talking about static long-lived video objects, for example, right? You have a long-lived connection that you are streaming to the local end user who's using mobile IP, right? Now this end user moved from one gateway to the other, right? Because you are doing this optimized forwarding, if you don't inform the web cache that this guy has actually moved out of my local context, he will continue sending it to the local coordination. That doesn't make sense, right? So you have to convey to the existing gateway that this guy has actually moved on to the next IOTA gateway. So there's an inter-gateway communication protocol where the session state is conveyed back and forth, saying the guy who was with you before is now with me. So the web cache is automatically instructed using packet filtering rules to send the traffic out on the network rather than the local foreign agent.
So the website will still be communicating with the web cache in the old.
Yeah, so that is the case. And of course, the longer you have your forwarding path, the more efficient it becomes. So yes, after a point, this can become inefficient.
How do you know what gateway to send the traffic to?
Oh, because you want the guy to register with the local gateway, right?
Right.
So the local gateway also knows where you came from in some sense. Because these guys, in our model, we have these gateways cooperating with each other. So they can query the other guys. Have you seen this guy before? Is he coming from any of you guys? Kind of thing. So this is somewhat of a proprietary solution in the sense we are creating an overlay of this gateway. But that makes sense, especially in a big hotspot. So if you are in a big library or in a big airport.
Oh, it makes sense if if one entity owns all the gateways. Right.
Yes, but even otherwise you still need some cooperation between the gateways to be able to convey the session state across the gateways as you move out of the context of a single gateway, right? So think of this gateway as one, and there's another gateway is deployed in another part of the WINLAB, right? As I move around into that guy's context, this guy now has to inform him that, hey, this guy was sitting on him and I'm sending him some data, right? So instead of trying to send it into this room, it will try to forward it over the wired backhaul into the wireless cloud in that other part.
But what if this gateway is in some other place, let's say it's in another port building or some other building, what happens then? Which is owned by, like you said.
That's a good point. So that's what I'm saying. So once you have this cases where you don't have an association between the gateways, then of course it won't break. Right? It won't work, and then it will break. So the optimization sort of works in the scenario where you have these gateways that are collaborating with each other, and the total footprint of all these collaborating gateways is fairly large. The assumption is that your mobility is not so severe that you're going to quickly go out of the coverage of all these gateways. But you're right, if it does happen, then you have a break in your connection, and that's sort of breaking the semantics of mobile IP.
So, okay, there are Cisco solutions available where you have multiple gateways. Like we are talking about inter-organization case now, long organization.
Yeah.
And there are Cisco gateways available where you move from one gateway to the other. Immediately you get an IP address. You can actually keep the same IP address.
Yeah, so actually I'm going to talk about that similar stuff that we have also done.
Yeah, in which case you can share the common cache if you have a common backlink. Let's say if you have a common wired link for these gateways, which is being served by the common cache, then there's no point in having different caches.
Yeah, the way we have done it is we have cache in every gateway. So, but if you have a single cache that serves multiple gateways, then you don't have that issue. But again, I think I need to understand the scenario that you're describing more clearly.
So it's like clearly more efficient in the sense, here you have one cache per gateway.
Yeah.
Let's say if you deploy 5 gateways, you will have 5 caches.
Yeah.
And then you will have, on top of it, you have all this overhead of informing or synchronizing between gateways or these message passing between the gateways.
Yeah.
Cisco has a very nice, if you see this Cisco access points, I don't know what is it.
The Orinoco, not Orinoco, the Aeronet.
Aeronet access points.
But the Aeronet thing you're talking about is called the WDS solution, though that's more at the layer 2. Are you talking about the wireless distribution system solution, the WDS solution?
Yeah, exactly.
Yeah, but that's again layer 2 forwarding, so that's not going to give you a whole lot of range unless you are doing Ethernet over POS kind of thing in a metro environment. Here the model is that you have a bigger footprint, large number of access points aggregated into a gateway. So there's another reincarnation of this box that is a 1U form factor. That's a much bigger gateway. So you can aggregate large number of access points into it. Assumption is that large number of access points hopefully gives you a larger coverage range, right? And if you have larger coverage range, typically WDS kind of thing doesn't scale very well because inherently it's layer 2 forwarding mechanism. So unless you start scale in terms of like limiting your layer 2 broadcast, or I think what I mean by scale is typically WDS I don't think has been made to work for more than a certain number of access points. At least the Orinoco specs that we are seeing internally, it's typically 8 to 12 access points. And I don't know how far they can be separated out, right? So what I mean is that if you have 12 access points and if they are not going to be that well separated, the coverage footprint of that is going to be limited, right? So if you are trying to cover a large amount of space, you most likely won't be able to use layer 2 forwarding across this large number of access points. That's what I'm saying. So
a question. Even if a mobile stays in one gateway, but it could be going in and out, suppose it asks for a 100 megabyte file, all right? Only when it's got it all can you basically remove that file from the cache.
yes, so you are sort of anchored on that web cache when the file is being served. Yeah.
And so you've got to probably store that file and then have some kind of aging algorithm to throw it away.
Sure.
How fast can you get access to a file, do you have any idea what that speed is? I mean, we talking microseconds or milliseconds and things? If you assume that a gateway might have, you know, 100 gigabyte memory, how fast?
That's all the standard benchmarking that you typically do in a web cache. So there are standard benchmarks available called Webstone.
Right.
So Webstone will typically, I think, give you there are different kinds of traffic types that you can think of. The standard caching objects, our cache is rated to be 600 HTTP per second in the full-blown implementation.
600, what did you say?
Per second HTTP requests that you can serve out of the box.
I didn't understand.
So think of the web cache as just a traditional web cache, and you have a measurement device that's blasting HTTP requests to it.
Right.
And the benchmark is sophisticated enough to ensure that you do enough refreshing of the requests and all that stuff. So based on that benchmark, you measure how many requests can it serve at any given rate. So what I'm saying is, now if you go to the web cache that we are using, it can support up to 600 HTTP requests per second.
600 per second.
And again, this is for traditional small object HTTPs. But now again, there's a benchmark for a larger object that you can go and get information on. Again, it's not off the top of my head, I don't remember the number, but if you want, we can get you those numbers too.
Okay, but I guess your answer is it's fast enough that the mobility is not going to be an issue.
Yes.
Right.
Yeah.
Okay.
And again, this is being served on TCP, so the TCP back pressure mechanism will hopefully stall it until the point you have successfully moved. And because the gateway to gateway communication is expected to be a high-speed backbone, the context transfer should be fairly swift.
The problem on the website, the problem would be an issue to have binding of the information to correspondent node, in other words, web cache. The route optimization is done by Mobile IOTA. So you don't have to do the same thing in the application layer. You should throw it on the right.
That second part I didn't quite understand. Repeat that.
Where you're actually eventually doing the route optimization. Right? Sure.
Yes.
But route optimization is already in place in Mobile IP. So why are you?
But I think the route optimization is for a different reason. I don't think. You can come and ask me offline because I have lots of stuff that I want to go through. Please come and bug me. I want to understand what you're saying. So, again, accounting. This is not a whole lot of stuff that I want to talk about. But the idea is that again, that box that connects 3G and radius accounting and allows the applications on the gateway, which are in the form of say mobile IP registration or the web authentication or DHCP address allocation. These events sort of drive the accounting events at the start and stop of accounting. So the mobile IP agent on the gateway or the web server on the gateway, they go and actually issue these accounting events. So those applications actually use a library that we have developed that then dumps the accounting records on the accounting table using the active session table, and then in the background it can be sent to any backend that you need to send it to. So the mobility client that we have, again you will see that when I try to do the demo, it supports mobility across multiple interfaces. So we have right now 802.11 G and the 3G1X RTT and eVideo, and also dial-up and Ethernet. So the user processes, user applications that are running, they don't see any break in their connection. Our software automatically keeps track of multiple networks that the laptop sees. It figures out which is the best network currently to sign on to based on certain things. And those certain things are the signal strength, it could be the policy that the user configures, it could be the priority that you have hardwired into the policy engine. whether there's a mobile IP agent available on a given network or not. Using these different factors, it figures out which network at any given point makes sense. And also it has inbuilt mechanism to avoid switching back and forth between two networks. So if you're sitting on the edge of two networks, it will try to do hysteresis-based filtering to avoid bouncing back and forth. So it has a bounce prediction algorithm built into it. And also it allows you to switch your ongoing IPsec tunnels. Typically, commercial implementations don't do a good job of coexisting with mobility. So our stuff actually does that also quite well. So there are three components to what we have built. So at the lowest level, we have all these different physical interfaces. So this is sort of the Windows very 10,000 miles high up view. So what we have built is a multi-interface mobility client that sits in the kernel. Then you can talk to this driver using the piece of software that we call as the multi-interface mobility client. And then there's a GUI that sort of allows you to interact with these pieces. And also it interacts with the IPsec client. So the whole software is about 45,000 lines of code, out of which about 13,000 lines is in kernel. And as you can see, these are sort of the parts that we have built. These are the existing parts. This is also existing stuff. And this has been extensively tested on XP and 2000, and we also have a sort of a beta version of this on Linux, if you guys want to look at it. And this is sort of the client interface. When I do the demo, you'll probably see a better, more details on this. So now, up till now, we talked about sort of the landline networks. Now, suppose you are the kind of user who doesn't care about Verizon, who doesn't care about 3G service. You have 802.11 at home, sitting on your cable modem. You have a laptop that has built-in 802.11. That's all you want to ever use in your life. And your lifestyle is such that you go to New York every day from New Jersey, spending an hour and a half in a bus. So you want to be able to access internet. Or you are, say, a small business who does a lot of conventions around, and you want to set up your own hotspot for demos or for secure access to your end users and stuff like that. Now there is this high-speed wide area wireless network out there. So how can you sort of bridge between the two? You are a mobile user who doesn't care to use 3G because you're not interested in spending $300 buying yet another card that you need for that. So what we have is a small box that we call Mobile IOTA that sits in the bus, essentially, or in the convention center that you want, and it uses the high-speed uplink in the form of EVDO. So the current network that we have here is 144 kilobits per second per user, but there's another variant that's EVDO and the EVDP variation that gives you up to 2.4 peak capacity and sustain anywhere from 400 to 600 kilobits. So when we try this box out in our network in Virginia, we see about 600 kilobits per second on the EVDO uplink. So you can aggregate Wi-Fi essentially into these EVDO links. That's the high-level idea. So you are using 3G as a backhaul. So end user doesn't really see any of that, and it allows you to incrementally deploy 3G, and also makes it easy for, say, hotspots that may not initially see traffic. So instead of going and wiring up this hotspot, you could use a network element like this, which you go and deploy. If you see more traffic, you can upgrade the uplink capacity out of that hotspot. So the two applications, as I said, are the mobile hotspot and portable hotspot. So we call it either Wi-Fi on the go or Wi-Fi on the move. And there are several applications. One interesting application would be making this into like a sensor network gateway. So when we're talking to people in Boulder recently, Boulder people have actually a sensor network group that is doing work on forest fires. And one of the big problems that they have is that they deploy sensors in the forest, but they don't have a way to remotely monitor them or remotely collect the data from the sensor clouds. So potentially a box like this makes sense because it will sit there and remotely you can make it into a sensor network gateway. So again, this box supports different kinds of client. You could either come and use only in the simple IP mode, so you do DHCP to this box and you access network as if you are accessing it at home, or you could be accessing it in the mobile IP mode. So you are still a Verizon customer and using the 802.11 hotspot and getting authenticated to the Verizon backend. And one key thing to note is that as the train or the bus moves, actually this box that you have here, the uplink to the PDSN, that is actually undergoing a change in its IP address all the time. So when I go from one PDSN to other, my IP address is changing or my foreign agent is changing based on what mode the box operates in. So if the box is operating in the mobile IP mode, the foreign agent changed because your PDSN changed. So as far as the end user is concerned, this becomes transparent. You see nothing but a new foreign agent. So as if, even though you are physically not moving in with respect to the gateway, your foreign agent change transparently to you. So you do yet another registration and things just work transparently, they work fine. Another key important sort of engineering issue is that when this backend's address changes, this backend actually has to be authenticated to the radius server of the provider that corresponds to this particular backend. And because this address keeps dynamically changing, the radius server in the gateway now becomes an interesting scenario. There are no deployments out there in the radius world where the radius server's outgoing address is continuously changing every so often. So you have to sort of account for that scenario by doing certain things. And I wouldn't want to go into details of that, but if you start thinking about how to make this work, you will come up with these problems. So there are several enhancements that we are talking about and some other work that you guys are doing is sort of relevant in this space. So how do you improve the uplink capacity of the mobile IOTA? One is you potentially have multiple uplinks on the box that correspond to different providers, and you are doing dynamic flow-based striping. So when there are only 2 users, you use only one uplink to Verizon. But if now 20 users are there and the uplink is inadequate, you're going to dynamically go and activate another uplink to say Sprint or AT&T or to the same provider. So you dynamically can do link striping, which is somewhat different than traditional link striping because the other endpoint is not doing the same striping. But we are working on that aspect also. Also, one thing that we are talking to our base station folks is potentially doing proprietary modifications for doing e-video scheduling, because you are getting these large fat aggregate pipes coming out of the mobile hotspot. You could treat them differently and give them certain quality of service and hopefully make performance even better for the IOTA boxes. Also, certain antenna technologies like MIMO, they are very expensive to deploy on end clients. Now you can get those antenna technologies developed specifically for these kind of boxes first, so the end user doesn't have to go and modify its end devices. So the cost of adding these antenna techniques based on blast or the rooftop antennas, that big efficient antennas that you can put on buses and trains, that can make your performance even better for these boxes. And some of this work is sort of ongoing. So that's sort of how much time do you have? My goodness, yeah, that is stuff. So maybe I want to quickly go through a couple of other parts that we have done. Now, MobileNAT is a new piece of mobility technique that we have developed, which tries to sort of improve upon the existing mobility techniques. And there's a paper out there in WMASH workshop, and it's invited for a journal. So if you guys want to know more details, they are all there in the paper. I'm going to try to sort of cover some of the basic ideas. And again, this technique is relevant for things like sensor networks, where the sensors don't have much capability, but they may be moving around, and you still want to support mobility efficiently. So here the idea is that you have a bunch of domains which are sort of delineated by anchor nodes, which we call as address translation nodes. And the mobile node is sort of moving across these different domains. And it has 3 different kinds of sessions, sort of an internet session to a public address, internal session to a domain node that's sitting in the same anchor node domain, and another inter-domain session that goes from the mobile node to another mobile node in another domain. And the common case is that when you are accessing a hotspot, you are not really offering any long-lived service. You are not running a web server that other people necessarily want to contact. The model is that 90% of the access is you going out and accessing the network. So the common case behavior is that you want to preserve the kind of sessions that we talked about rather than any incoming session, with the exception of potentially voice or IP. But that can be taken care by using SIP mechanisms. So in our model, we are interested in supporting mobility for these kind of sessions. And again, you want to have this technique that can work independent of underlying access technology. So it should work for 802.11, 3G or any network. So this is primarily a layer 3 mobility mechanism. So the one problem that you have with the existing mobility techniques is that things like, for example, Hawaii or cellular IP, all those micro-mobility techniques require you to do significant changes to the routing infrastructure. Also, mobile IP, for example, requires you to deploy for subnet foreign agents. So the one big claim that we have is that in our case, we don't require any routing infrastructure updates. The only thing you need to do is modify the egress router on your domain, the so-called anchor node. And because most of the egress routers anyway support firewall and routing functionality, implementing some of the stuff that we are doing is very easy. And we also have a working implementation of all of these things. So I'll spend about 5 to 10 minutes trying to at least give you the idea of the proposal. So the problem with IP address is that it's sort of overloaded. It's doing host identification and it's also doing the routing for you. So that same address is being used for forwarding the packets also. There is no disconnect between your host identification and routing. So it's sort of overloaded identifier. And a TCP connection that you have typically is characterized by 5 tuples: the source address, the destination address, the source port, destination port, and the protocol ID. So this 5 tuple is maintained at the mobile node and at the end host. So anytime you move, your physical address is going to change, and that association, the 5 tuple, is going to break on your end. And unless it's proportionately changed on the other end, your connections are not going to continue. So what we are proposing is that you use essentially 2 addresses. One is so-called virtual IP address, a fixed host ID that is exposed to the higher level applications and the protocols. So if you look at the stack over here, IP and above, they're exporting a address that is a constant virtual ID. So when you do DHCP, you get a virtual identifier. And as you move around, your actual physical routable address will keep changing underneath. And using a special software layer that we call a shim layer, you will not see this change. So the endpoint will always think that it is talking to the virtual identifier AV. And again, because we are trying to account for the scenarios where you have hotspots where private address spaces are common, the AV, the virtual address and the public address, they can be either private or public. So you sort of get these 4 different conditions, and we sort of account for all the 4 cases. So just to give you a quick animation, what's going on is that initially you set up a connection to CNN, and you, as far as the application is concerned, it's talking to this address AV. So this is the tuple that it maintains. And the CNN, before I go to CNN, let's see what's happening here. So the shim layer is actually taking this address AV and it's translating it to your current physical address AP. So that's where it's doing the NATing internally within the host. So the traffic that is flowing out carries the address AP1 and the source port. Now as you move to another domain, and before the packets go out, they are again changed by the anchor node of the domain. So you are changing the address from AP to the outgoing address of AN. So CNN always thinks that it's talking to this address. So as far as CNN is concerned, the connection is anchored on this host. So when you move around, your address changed from AP1 to AP2, and again the shim layer took care of translating that appropriately. And as far as the CNN is concerned, nothing really changed, because the traffic is still, not good. As far as CMN is concerned, nothing really changed because you're still anchored on that external node AN. So the name sort of MobileNAT comes from the fact that you have a NAT going on in a mobile node, and also the network NAT that's going on in the anchor node is used to support mobility. So as you can see, the routing infrastructure here remains completely unchanged.
Like Sony had a proposal in the early days of mobile IP, which looked pretty much identical to that one.
Oh, okay, we haven't.
It was like many years back, and I was wondering if you have seen that and how yours would differ to that.
I haven't, but I certainly would like to see
I
the
just
reference.
remember it was like I saw that many years back.
Okay.
It looked identical to that.
Okay. Yeah, our motivation is primarily because we support that thing in our box. So think of this box as deployed in the airport, and your PDA, you are roaming around in this airport hotspot. Now there is no need for you to actually go to a remote home agent somewhere in San Francisco where you're in Newark Airport, right? You need a micro-mobility technique that will work well in that hotspot and make your handling of the private address space also efficient. Because in our case, both AV and AP can be completely private address.
On the device or in your access point?
Good. So that's what I was going to emphasize. So there are two ways of doing it. If you put it in the client, then of course you need client modification, especially if it's a PDA, that might be too much. If it's a sensor, it may be too much. But if you implement it in your subnet router, then you can carry the same address anywhere you go. So you give one address at the time when the device comes online, and then it can carry the same address all over the place, as long as the access elements are consistently updating the current state of the host as to where they are attached.
You could potentially have a conflict there. To make sure that you don't using the same address across.
Refer to our paper, virtual address aliasing. So we talk about that aliasing problem and how to solve that. And yeah, so there may not be the best efficient solution out there for the aliasing problem. That can be solved potentially by management. You could do address allocation that is guaranteeing minimum number of conflicts. You could do some of the techniques, but again, you're right, 100% guarantees are probably not going to be possible where there would be no conflict at all. That is not possible to do. So the paper discusses some of the issue that you are bringing up. Good point. We call it sort of virtual address aliasing because the same address may be allocated in a different domain, and when you walk in there, you will have a conflict, especially in the case where the access elements are implementing the NATing functionality.
Can you use MAC address for AV? Because MAC address is unique for each device.
Our technique, as I said, is layer 3, so we want to deal with only IP addresses, so we don't want to deal with any MAC addresses because we want to support mobility at network layer. So we never even bothered thinking about the way you are saying. There may be some advantages, but I haven't thought about that way of doing things.
AN is for domain.
Yes. So under the domain, you could have a big routed network, or you could have a layer 2 cloud also.
And moving from one domain to the other?
That is coming up. So again, these other things sort of handles all the different cases of exposing a public virtual address and not exposing a virtual address. All that kind of stuff is there. Another alternative is from the anchor node to the mobile node, you can either do translation or tunneling, and again that gives you certain advantages. In wireless world, especially in 3G links, tunneling may not make sense. So that's one advantage why you actually want to use a technique like NAT. That's again. So your inter-domain thing is coming up after this slide. So here what we're talking about is the intra-domain section. As I go from one domain to the one part of the domain to the other part. So this mobile node in the domain is talking to a correspondent node in that same domain, and that correspondent node in this example is a static node. So they both have a virtual and physical address pair. And the way we have solved this problem is that the routing within this domain, if you want to handle intra-domain mobility, is set up such that all the packets that are sent to the virtual address are always anchored on the anchor node. So the routing is configured such that it will always get forwarded to that anchor point. So when correspondent node is sending packets to the virtual address 128.0.2, it gets forwarded to the AN and then it gets forwarded to the MN. And then this can be taken care by doing source NATing and destination NATing. Again, this sort of gets somewhat finer point. Some of this is discussed in the paper. So if I move, and the reverse traffic from the MN again goes to the anchor point, right? Now if I move from one part of the domain to the other point, where my physical address changed from 1.5 to 2.7, the anchor node, that node still continues sending traffic to my virtual address, so it always comes to the anchor node. And the anchor node knows my current attachment point, so he appropriately forwards that traffic to me. And for the reverse traffic, you never necessarily need to come to the AN, because that, in this case, that guy is static, so it can get forwarded by regular IP forwarding. And then you could do peer-to-peer communication to optimize this forwarding bottleneck if you want to. Again, this is somewhat secondary level detail that I think I'm sort of short on time. So the interdomain mobility is, again, we have a concept of home NAT and visited NAT. So when you move from one domain to the other domain, the existing domain where you started all your connections, that becomes your home NAT. That anchor node becomes your home NAT. And then you are essentially asking that home NAT to become your dynamic home agent. So for all the connections that you started in that domain, that anchor node is your dynamic home agent. And when the connections go away, that anchor node ceases to be your home agent. So the advantage of this approach is that, unlike in mobile IP, where home agent allocation, even if it's very dynamic, is typically at the time of authentication or the registration. Here, it sort of is very adapted to your own traffic. The more number of connections you set up in a given domain, for those connections, the anchor node of that domain becomes your dynamic foreign agent. So it adapts far more rapidly, and also it automatically always has optimal routing property, because the anchor node of the domain that you exist is your home agent. So your forwarding is more optimal. Of course, if you have these forwarding legs that get too long, then you have to have a policy mechanism as to how far you can stretch this out. And this is much like what happens right now in terms of how voice calls gets handled in cellular networks. The network where you started your call, that MSC is your anchor MSC always. So when you keep moving from one MSC to the other, the traffic is always forwarded from that anchor MSC. So this is sort of very similar to that approach. And again, here the reverse traffic doesn't have to always come to the home NAT, it can directly go to the internet. So how this is implemented is shown over here. We have this notion of relays per subnet, which already exists in all Cisco routers that you can deploy. So the end host basically does a DHCP request that gets relayed to a DHCP server, which allocates you both AP and AV. So in our current implementation, we modified the DHCP server to give you both these virtual and physical addresses. And whenever there is a change of physical address, that change of leads is conveyed to what we call as a mobility manager. And this mobility manager goes and reprograms the NATing rules in the anchor node device, the AN. So we have modified the Linux actually to be able to use a setstock option where you can go and play with the IP table rules and dynamically change them whenever you want to change them. So this is again a kernel level modification that we have. So as you move from one subnet to the other, the DHCP and the mobility manager, they collectively detect this mobility event and make appropriate modifications to the NAT. And there is already activity in IETF to define a well-known interface for this kind of control of middle boxes. It's called MIDCOM. So we are essentially using the MIDCOM framework. Okay, so, and again, all of this is implemented in that same common framework of the mobility client. As I mentioned to you before, we have this unified multi-interface mobility client. So that same GUI, you can dynamically select as a mobile IP or MobileNAT, and based on the domain policies or any of those things. So it just is a new piece of software that we created over there. Okay, and this is sort of comparison to existing schemes. So, now I'll stop after this Iota-Cluster thing. This is sort of very similar to what Ray is working on, the multi-hop forwarding mechanisms to deploy. So the motivation here is that your current 802.11 is very range limited. You have 300 to 400 meters of range. Also in a 3G network, the farther away you are from a base station, the poorer throughput you are going to see, more battery consumption you are going to see, and effective cell throughput is probably going to be limited by such diverse user population. So now can you exploit the dual radio capability of the end host? So the motivation that was sort of the motivation, and sort of the solution that we came up with is what we call as manage, secure, ad-hoc infrastructure. So the idea is that you have two kinds of boxes, the relay IOTAs and the gateway IOTAs. The gateway IOTAs are the ones that are connected to the internet, either a wired uplink or a wireless uplink. So in our case, we are looking primarily eVideo as one classic case, where you can think of it as a golf course, where I go and put a card that has two boxes with eVideo uplink, and then I have another card parked that have relay IOTA boxes, which the customer always talk 802.11. To this end, they talk 802.16 or 802.11 A or B, and they together with the gateways sort of form this auto-configuring, self-aware, power-optimized, and appropriately frequency planned forwarding infrastructure, sort of a packet transport infrastructure. And somewhere in the network, there could be a network management entity that one can run and figure out what's going on in this cloud, the current status. And you could either through management mechanisms or through dynamic mechanisms change routing in this to be aware of load. So for example, on a golf course, when a bunch of people move from one place to the other following Tiger Woods, all of a sudden load on certain relay nodes may be higher, and you may have to do appropriate traffic balancing to get decent performance for all the people who moved. That kind of so somewhat of a contrived example, but that's sort of the scenario. So this prototype is also sort of implemented this using modifications to a demand-based reactive routing protocol, the AODV protocol. And again, because it's all Linux-based, it again runs on that simple platform that we have. And so there's a bunch of issues that I sort of already talked about briefly. How do you handle mobility in such a network? How do you do packet forwarding efficiently? How do you do auto configuration, gateway discovery, power management, frequency management, all those kind of things. And the MobileNAT that we talked about nicely maps into some of these things, because the relay nodes now run the MobileNAT client. The gateways become your anchor node, and a client can carry a constant IP address across all these relay nodes without really having to run a client software. Right? So that's about, I'm going to skip this shared key exchange business. There's an internet draft available, and we are trying to sort of harmonize this. There's another scheme in IETF called EAP-RG, and there are similarities with our work and their work, and we are talking to these people from Intel to sort of see if we can combine these two schemes. And the idea here is that you have a common shared secret on your device that is used for authenticating across all networks, and to be able to do dynamic key derivation, also do mutual authentication, and there's a notion of path authentication. Both endpoints should know what entities the authentication traffic is going on, so they know that these entities are trusted. So our scheme sort of supports that feature. So maybe what I want to do is try to show you the demo. So sometimes what happens is that because the box has been sitting idle, the uplink can sometimes go into a dormant mode, especially from the other endpoint, from the Verizon's network point of view. So sometimes there may be some delay. So the thing to do is sort of I can do a ping and kick it, but now that I've explained to you, I don't need to. So this is sort of the top level interface that you are seeing. So what has happened now is this multi-interface mobility client just detected the 802.11 that is being put out by that box on its 802.11 access side, and it also has a 3G card in this. So it's detected Verizon's live network also, and as per the policy that we have configured, right now it has registered on 802.11. As you can see, this colored thing over here, that's saying that 802.11 has higher priority because it has higher speed, and I see it very close to me, so it selected that, and it has gone and done mobile IP registration. So it says I'm at a foreign network, that's my mobile IP home address, that's my network access identifier now, and that's the current foreign nation that I have configured to, and that's my registration lifetime. So he has connected to that, and here you can see that the current 3G1X connectivity is about 115 kilobits, but that's sort of misleading because that's typically the serial connectivity. Hopefully when we do the file transfer we can see what is there. So I want to do a FTP here over this. Now I'm going to transfer sort of a big giant file. So the current speed is in this location doesn't seem to be that great. When I did in Colombia, I got pretty close to 110 kilobits. Right now I'm getting about 16, 20 kilobits, which is not necessarily that great. We are sort of doing.
Where is that file sitting? On that box?
So the file is actually connected to a remote server in home desk. So the way, actually maybe I need to explain the configuration just a bit. So what I have is that box has 802.11 hotspot built into it. So assume as if I came into this place, I want my own hotspot. I drop this box in and I have my own hotspot because it has an uplink to the Verizon network. Ideally it has an EVDO link, which should be 2.4 megabits per second. But right now, because in this area we don't have a video, I'm actually connecting via 1x RTT to the Verizon live network. So it's going to the nearest base station of Verizon, to their PDSN, to the internet, to home desk. That's how I'm connecting from the laptop to the box. Box is going through that.
The box is also going. What was the box connected to the fixed?
No, it's connected to the Verizon network.
The same as that.
Yes. So right now, what I'm trying to show. So let's consider two scenarios. One is my client is capable of both 802.11 and 3G, right? In that scenario, ignore that box for the timing. Think as if it is connected to a landline, right? So I'm coming from outside WINLAB into the WINLAB building. As I walk in, my laptop detects that there's a better 802.11 connectivity out here. It will automatically switch over to 802.11. It will hunt for a mobile IP agent. If it finds one, it will register with them. And any connection that you have active, that will continue transparently in the background.
Including voice connections also?
That's a good question. Who asked that? Here. Yeah, so we have to, that's actually the work that currently we are doing. We're trying to test the voice over IP over 802.11 in that setup. First of all, 802.11 is not optimized for voice, so we don't have a very good answer for that, saying, oh yeah, we can handle voice. We are trying to figure out how well we can do, and that's sort of ongoing work. Right now it's primarily for data. So we want to support
to consider the handoffs between voice handoffs between these two systems, 3G and 802.11.
You should work with us then, because that's what we are currently doing. So how to support two kinds of voice handoffs, voice over IP as well as circuit switch 3G to 802.11 voice IP, how we can potentially do that. We can talk more about it, and I can give you an idea about what we are doing in that domain.
Is there an economic reason to do that? I mean, the voice is very delay sensitive and things, and to the degree that you have several voice connections going on in a hotspot, you would may preclude somebody driving through that wants the 50 megabyte file, which is what it's good at.
Yes, so you probably need to have 802.11 E support activated on the access points to do strict guarantees. Otherwise, right now, you may see conditions where I initiate my call gets transferred, but somebody came along and fired up a big FTP, and that can kill you, and it will kill you, I think. And that's what some of the things we are trying to characterize, how bad it can get. If you have to operate in a legacy environment, how bad things can be. If I go to 802.11i or 802.11e, how good things will be. Some of these things are being currently worked on. I don't have enough slides here to sort of go into that right away. But again, offline we can go into that.
I don't see the economic incentive to do that, to allow the voice at all.
Economic incentive is actually kind of interesting, primarily because, say, you take a customer like Singular. Singular's one problem is that they don't want to do right now huge amount of base station deployment. But they do have, via SBC, a landline business that they are deploying as DSLR. And they want to connect these access point hotspots on those DSL links. And if and when possible, transfer a call out of wide area wireless onto this infrastructure, because that saves them the spectrum on the wide area wireless. Okay, so these are some of the short-term considerations. In the long run, you are right, there is no motivation for transferring a circuit switch call on a 802.11 voice over IP. And especially if your entire access network becomes more and more IP-based,
especially if you have a situation where, in a high mobility environment where you have just a few seconds for the entire session, you've got to basically have capacity sitting there.
A comment here. Jim, here is a good example when you, for example, want to do this handoff to 802.11. Suppose you're considering a mall where a lot of people are slowly moving and they're talking. It's actually cheaper to place an expensive access points throughout the entire mall than to increase the density of the 3G base stations. So in that case, actually it's beneficial that most of the traffic goes to 802.11, and only the people who walk in or leave the mall but still talking inside their cars, they take advantage of 3G.
Okay, so what I want to quickly do now is show you. So that case was that when I was walking from outside into WINLAB building, where the client who is dual radio automatically figured out it wants to switch over to 802.11, right? So because I'm not going to walk out of this room, I'm going to manually simulate the handover. So I'm going to put this into manual mode and switch over to 3G, and let's take my left port. So what now I'm trying to do is switch over from that 802.11 hotspot that I connected to my actual 3G connection here. And if there's enough signal on this, I may be able to do that. We'll see if it goes. Did I do this setting? There we go. So now it's operating in the so-called co-located mode of mobile IP. And as you can see, this switch from here to here, and it has already showed the connection, and here is the handoff. So you have changed the traffic from your 802.11 to 3G, and your FTP should have continued without any hitch. There are some issues that we see with that card over there, especially with the Linux driver, that sometimes the Windows driver gives you better performance than the Linux, and that's something we are talking to the Sierra Wireless people to figure out why there are these driver issues that we face. But that's a good observation, that the client is actually seeing better throughput on the 3G than that box is seeing right now, because of the very fact that this is a Windows driver, that's a Linux driver on that box. And these kind of funny things happen when you start actually trying to build something.
So the IP address in this network is the same as coordination?
Yeah, because you're still in the mobile IP mode, so it's carrying the same home agent address, or rather home address, but it's registering to a different foreign agent. So right now, when I was talking to this 802.11 over here, actually there's two things going on. So let me draw this. This is your 802.11 to this box, IOTA, mobile IOTA box. Now this guy is talking to the Verizon PDSN. And this here on this interface, it can operate in simple IP or mobile IP. So if I operate this in mobile IP, actually there's a foreign agent here, and there's a home address for this interface that is doing for mobile IP here. Now my laptop over here also has a home address. If I go in mobile IP mode here, the home address of this guy, and there's a home agent somewhere in the Verizon network that talks to me, my home agent, right? So my traffic is getting forwarded to him, and this interface may have a different home agent for all I know, but that is not visible to me. If I operate in simple IP mode, then it's just giving a simple IP address to it. There's no mobile IP on this interface. So as you can see, there's sort of this dual mobile IP that can go on in this particular case.
So that you observe the higher throughput somewhere else, right?
Yeah, on the laptop sometimes we see better throughput.
On the 802.11.
On the
You said at another university, I don't know.
Oh, eVideo. So right now,
it's not about drivers, I mean, right?
eVideo. So right now we have is a another 1x RTT connection. So this connection is the 1x RTT, and that is rated as 144 kilobits per second. So I can do better than 144.
Is it possible that it's so because of the bottleneck somewhere?
Could be, yeah. Yeah, very, very valid point. There could be a bottleneck in the network also, right? The internet itself may have a congestion point that I am trying to go through. Yes.
But there are driver issues as well.
We know that there are driver issues. So, because in both cases, most likely we are going to the same PDSN. Both transfers are probably facing the same congestion point if there is one out there in the internet, right? So my guess is it's primarily the driver issue probably showing up in terms of the amount of distance that we are seeing. So if you use eVideo, then this is actually fairly good enough for roughly 10 people in a hotspot to use simultaneously. We have tried some of these things. Up to 600 kilobits per second is fairly good link to multiplex into about 10 people.
I just have a question. Like, suppose we need to watch a real-time application, say like a movie or something. Theoretically, which one would be better? Is it 3G network or
Yeah, actually what we are saying is, now suppose this box is deployed in a train, right? And you have so-called personalized audio application, right? The box can proactively, based on your profile, download things in the background and do content caching for you. But if you want to really prime a live event, then we haven't done any tests to really tell you authoritatively that, oh, one is better than the other. So some of the measurements and experimentation is sort of going on right now. So, maybe what I want to do is show you a simple IP mode of operation also. So I'm going to cancel this now. And actually, if you want to, just for the sake of it, we can try to switch over again to 802.11. So in the background, it's now going to try to switch over to the 802.11. So it has sent the request, and this guy's uplink, especially if it goes dormant, then it takes longer. So there are sort of means and ways to keep it. Looks like it is 9.10 right now. Yeah, switched over there now, as you can see. Went from here to here, and it's registered to the formation over to that box again.
Is the delay small enough to prevent anything happening?
Yeah, so right now I think don't pay too much attention to the delay, primarily because of the fact that we have to still fine-tune the uplink interface. Because the uplink interface really goes into a dormant state if there is no traffic. And that is getting factored into a registration because there aren't that many users right now. I mean, I'm the only user right now, right, on that gateway. But if there are more people active, probability that the uplink goes dormant is diminished. So your registration is going to go through relatively quick. And that's what we notice actually, that if we run a background ping traffic, it goes through quite fast. But then I need other machines and stuff like that to do that. So.
Does the mobility box, Iota box have routing capability?
Yeah.
What if that Iota box move to another? Another
PDSN.
Yeah.
Yeah, so it automatically, transparently, it will do formation registration in the background.
And what about the other mobiles?
The mobiles are static in relation to the box. So if they are doing simple IP, they will notice a momentary glitch in their connection. If they are doing mobile IP, they of course have to go and do additional registration because the foreign agent on the box has exposed a new address now. So it's as if even though the laptop is static, it's effectively moved to a different node. So it's like you are static related to a moving object, but from the perspective of the other network, you are actually moving.
In current cellular network, there's no mobile IP, right? The mobility is handled by the link layer code. So what if you use...
There is mobile IP in certain networks, so you go to Sprint, actually Sprint default operation mode is mobile IP. So there are two ways of mobility. One is that you are moving inside a PDSN. So you're going from one RNC to the other RNC. So your radio link protocol connection is breaking and coming up. So that is transparent to your PPP. And because PPP doesn't break, your higher level protocols don't see any break. They just see a freeze on the connection. But if you go from one PDSN to another, your PPP connection will have to be restored. And based on how your OS implements it, most likely, if it's a Windows implementation, the PPP connection will break, the entire socket will come down. The entire interface will come down. And then you will lose all your connections. So I'm pretty much done. I just want to show you one last thing if it works. One problem we have is actually this Toshiba 802.11 interface sometimes was flaky. So now what I'm trying to show you is actually the notion of a portable hotspot without any special software on this. So you are doing web authentication to this box. You came in, you did simple IP to this box, and this box gave you a IP address, and you're just accessing the network without really moving. So this is a good application like in a convention center, where you go and put this box out in the convention center. Your people came and start accessing internet using that box, using the wireless uplink on that box, without needing any specialized software. I suppose you get the idea. Maybe I'll show it to other people who want to hang around, and but in the meantime, we can conclude, I think.
All right. Thank you.
Thank you.